Hi everyone, in this lesson, we'll be learning about the relationship between Kepler's third law of planetary motion, Newton's law of gravitation, and the concept of centripetal acceleration, especially how these three works together in circular orbits. These ideas are very important in understanding how planets, moon, and satellites move around larger bodies like the Sun or the Earth. The main goal of this lesson is to understand how these three concepts are connected. We'll explore how Kepler's law helps us describe a planet's orbit, how Newton's law of gravitation explains the gravitational force keeping it in orbit, and how centripetal acceleration describes the motion that keeps an object moving in a circular path. By the end of this video, you will see how all three laws fit together perfectly to describe motion in space. Let's start with Newton's law of gravitation. This law tells us that every object in the universe attracts every other object with a force called gravity. The size of this force depends on two things: the masses of the objects and the distance between them. If the objects are massive, like the Earth and the Moon, the gravitational force is strong. But if they're far apart, the force becomes weaker. The mathematical form of Newton's law of gravitation is F equals G times m1 times m2 over r squared. Here, F is the gravitational force, while G is the universal gravitational constant. M1 and M2 are the two masses, and r is the distance between their centers. This equation shows that gravitational force increases with larger masses and decreases when the distance gets bigger. It's the reason why planets stay in orbit. Gravity pulls them then inward while their motion keeps them moving around the sun. Now, let's connect this to centripetal acceleration. This is the acceleration that keeps an object moving in a circular path. It always points toward the center of the circle. That's why it's called centripetal, which means center seeking. The formula is A equals v squared over r, where v is the speed of the object and r is the radius of the circular path. We can also find v using v equals square root of gm over r, which shows that the speed depends on the gravitational pull of the central body. Without this acceleration, objects would just move straight instead of orbiting. Let's talk about orbital period, or the time it takes for an object to make one full orbit. The formula is g equals 2 pi squared of r cubed over gm. For example, if a satellite orbits Earth at a distance of 7,000 kilometers from the center of the Earth, and the mass of the Earth is 5.27 times 10 raised to the power of 24 kilograms, we can use this formula to calculate how long one full orbit takes. This helps scientists plan satellite paths and predict how fast they should move to stay in orbit. Now, imagine a newly discovered exoplanet orbiting a distant star. If the star's mass is 2 times 10 raised to the power of 30 kilograms and the planet's distance is known, scientists can calculate the orbital period using the same formula. T equals 2 pi square root of r cubed over gm. Knowing how long the planet takes to orbit its star helps astronomers understand its temperature, seasons, and whether it could possibly support life. Let's move on to Kepler's third law of planetary motion, also called the law of periods. It states that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. In simple terms, the farther a planet is from the Sun, the longer it takes to complete one orbit. That's why outer planets like Jupiter, Saturn, and Neptune take many Earth years to revolve around the Sun. In symbols, Kepler's third law is written as T1 over T2 squared equals G1 over G2 cubed. Here, T1 and T2 are the orbital periods of two planets, while D1 and D2 are their average distances from the Sun. This relationship helps scientists compare planets. If you know one planet's distance and period, you can calculate another's easily. Apply that. Earth is one astronomical unit, or 1 AU, away from the Sun, and it takes 1 year to orbit. Jupiter, on the other hand, is 5.2 AU away. By using Kepler's third law, we find that Jupiter's orbital period is about 11.9 Earth years. This shows how distance and time are connected. The farther the planet, the slower it moves in its orbits. So now, let's connect everything together. Newton's law of gravitation explains why there's a force that pulls planets and satellites towards the center. Centripetal acceleration describes how the force keeps them moving in a circular path. And Kepler's third law shows the mathematical relationship between their distance and orbital period. Together, these three laws describe the beautiful and balanced motion of objects in space, from satellites orbiting Earth to planets revolving around the Sun. That's it for today's topic. I hope you learned how these three important laws, Kepler's, Newton's, and centripetal, work together to explain orbital motion.